Hello. Today, we're going to talk about Einstein's special theory of relativity and what it means in the context of everything we've learned so far. So for over 200 years, we felt really good about three big ideas in Newtonian mechanics, or what we call Newtonian mechanics. And those are Newton's laws. Objects at rest or in motion tend to stay at rest or in motion unless there's an unbalanced force. When the forces are unbalanced, we see objects accelerate. The harder you push the object, the faster it can become, or the faster it'll slow down. And the more massive the object, the tougher it is to make it get faster. And for every action, there's an equal and opposite reaction. Or if you were paying attention in momentum, change in momentum of a system of objects is zero. We've accepted this for a pretty long time. But there were cracks in this theory. It turned out that when you got into moving at faster and faster speeds, Newtonian mechanics began to break down. What are the implications of Newtonian mechanics? Picture yourself on an enclosed train car moving at a constant speed. So you're not getting any faster or slower. Any objects you're holding in your hand are moving at the same speed you are, and we're not worried about air resistance because we're in an enclosed train car. You take an object and you throw it up into the air in front of you. How does it look to you? It should come up and come right back down into your lap if you're moving at a constant velocity. But how does it look to someone outside the train car? Outside the train car, they see the object move in a parabola, right? So to your perspective, you are not accelerating forward. You threw the object straight up and straight down, and it landed in your hand. To an external observer, the object was launched with a forward velocity and a vertical velocity, and so the object moved in a parabola. The laws of physics are the same for observers moving at steady speeds relative to each other. You may have had this sensation before if you're pulling into a parking space and the car next to you is pulling out, and all of a sudden you go, oh my gosh, I'm still moving forward. But they're actually moving back and you're stopped, right? Our observation of the laws of physics, as long as we are moving in what's called an inertial constant velocity reference frame. An inertial reference frame is a constant velocity reference frame. All of the laws of physics should apply to any observer moving at relatively steady velocities to one another. So now think about this. We are again going to ignore air resistance. I'm driving in a car moving at 30 meters per second. You're standing by the side of the road watching me go by. After I pass you, you throw a frisbee at me at 30 meters per second. How long does it take the frisbee to catch up with me? Can the frisbee catch up with me? Again, we're ignoring air resistance. If I'm going 30 meters per second and the frisbee is going 30 meters per second, can it ever catch me? Or will it just stay behind me at the exact same spacing the entire time? What happens if you throw the frisbee forward at 40 meters per second? Then can you catch up with me? Or then can the frisbee catch up with me? Well, yes, it can. Because how fast is it relative to me now? I'm going 30 and it's going 40. Then relative to me, it's going 10. What if I throw a frisbee forward at 20 meters per second? How fast is that frisbee now? If I'm moving at 30 and I throw the frisbee forward at 20, it's now going 50 meters per second relative to you, right? Think on that for a couple minutes. Think about that, those mathematics, draw diagrams if you need to. All right, but so now let's suppose that you're in a car moving near the speed of light. If you turn on the headlights, what happens? This is the difficult question. So what happens if you're moving at the speed of light, you're riding in a car moving at the speed of light, and you turn on the headlights? What's going to happen then? According to our frisbee example, the light should come out at twice the speed of light, right? If I throw the Frisbee at 20 and my car is moving at 30, the Frisbee is moving at 50. If my car is moving at the speed of light, c, and the headlights go on, pushing light out at the speed of light, c, then the speed of light should be at 2c, right? Well, there were some things happening here that were important. Prior to Einstein even coming onto the scene, the speed of light had been experimentally determined to be in the vicinity of 3 times 10 to the 8th meters per second. Just 20 or so years before Einstein began looking into this, James Clerk Maxwell had actually demonstrated that light is a wave with both electrical and magnetic properties. He came up with his 4 equations that pretty much define the behaviors of light as varying electric fields and magnetic fields that are moving through space perpendicularly to one another. And one of the things that came out of this was that the speed of light is actually equal to 1 over the square root of the product of the permeability of free space and the permittivity of free space. These are quantities that can be discussed in more detail later, but they're certainly worth a Google in the meantime. But this connection between the speed of light and these 2 constants that we had already determined through other means was very significant in defining the wave nature of light as being both electrical and magnetic in nature. Also, prior to Einstein were Michelson and Morley, who together executed the most famous failed experiment in all of history. So this is a good opportunity to tell you to remember that science is about learning how things work, not necessarily about being right. Sometimes when we do science, we don't always prove the thing that we set out to prove. We actually prove quite the opposite, or something that we weren't expecting at all. So Michelson and Morley set out to prove the speed of the ether. So the speed of light was a known constant at this point. This was a value that we had determined, and it was widely believed that light was a wave that required a medium to travel through. And that medium in space was called the ether. So Michelson and Morley's theory was that if we could shoot light out in the direction of the ether, and we could send another beam of light out perpendicular to that, then the light moving in the direction of the ether would be carried by the ether, and the light moving perpendicularly would be unaffected. If we could reflect this light back to one location, then we would see an interference pattern, right? Like we talked about last week, we would see an interference pattern between these 2 beams of light. And if we could measure the shift in that interference pattern, then boom, we can figure out the difference in speed of the one light wave versus the other light wave. We will see a shift in the fringes, and we will be able to figure out the speed of the ether wind. So Michelson and Morley set up this experiment. Worth noting, for being the most famous failed experiment in history, it was an apparatus very much so like the Michelson-Morley apparatus that helped us to discover gravity waves just in the last 10 years or so. So they sent out light from one light source, so monochromatic light, through a beam splitter or a partially silvered piece of glass that would reflect some light one way and allow other light to pass through. That light reflected off of 2 mirrors. And again, this is all oriented, these 2 paths of light are oriented perpendicular to one another and sent back through the beam splitter, where they will then recombine onto a screen. We should see a phase shift in the light, and we should end up seeing the light arrive back just out of phase, which will cause us to see a different interference pattern than what we would have seen if everything was interacting with the ether wind the exact same way. They actually kept their entire apparatus balanced in a pool of mercury so that it could stay level the entire time, and so that they could turn it and run trials with all of the light traveling into the ether wind and back. And ultimately, what they discovered after they sent this light through a beam splitter or a partially silvered mirror that will allow some light to reflect and other light to pass through, and then recombining this light and looking at these diffraction patterns or these interference patterns, they discovered no difference. There's absolutely no change. They could mathematically prove that the path that light took one way was longer than the path the light took another way. They could absolutely prove that without any issue. What they couldn't prove was that it had any effect on the light waves interfering with one another. Every time both beams of light arrived back with the exact same speed, which meant two things. One, that there's no ether. Sorry, everybody. I know it's uncomfortable, but we are in fact just barreling through the vacuous emptiness of space. There is no ether. And two, light is unaffected by the direction it's traveling in, by the winds that may carry it. Light, in fact, has an absolute speed. We can send light out and bring it back. We can alter the distances that light travels, and every single time it arrives back exactly in phase, its speed unaffected. So this was very upsetting to people. Our general understanding of how mechanics works is that if you are moving with one speed and then you get into something that is also moving at another speed, you can combine those speeds. It's simple vector mathematics. The idea that you could take the speed of light and take a flashlight and put it on a boat and turn the flashlight on, and the speed of light is still the speed of light, not the speed of light plus the speed of the boat, was very upsetting to people. So enter Einstein. Einstein came in with the brilliant notion that time is actually quite relative. We've heard the phrases before. A watched pot never boils. Time flies when you're having fun, right? So time does seem to be relative depending upon the observer and the situation that the observer is in. These phrases aren't really particularly scientific. So what really was Einstein getting at, this idea that time is relative? Picture lightning striking two poles at the same time. Somebody standing exactly between the two poles will see both strikes at the exact same time. An observer on a train moving near the speed of light, though, will observe these strikes at different times. How did Einstein theorize that you could actually see both events at the same time? He imagined a double-sided mirror oriented at a 90-degree angle, and each observer was holding this in front of them. So right now, you guys can see two sides of my room, right? You can see this corner over here where I'm keeping my markers. You can also see over here with my other arm. You can see into two sides of the room. So if this is facing the observer, then theoretically, they can see both poles at the same time. So to an observer that's standing stationary exactly between the two locations, exactly between the two simultaneous lightning strikes, they see it happen in this mirror and they see it happen in this mirror at the exact same time. But for the observer that is moving through space, right, they see it happen a little bit delayed from the mirror that is moving away from the one pole, and they see it happen a little bit faster in the mirror that is approaching the other pole. So even though we have an observer that says the two lightning strikes are simultaneous, we have another observer that is completely justified in saying that the strike ahead of them happened before the strike behind them. This meant that simultaneity is not an absolute. two events can occur at the exact same time for one observer, but be perceived differently in time by another observer. Thus, the perception of time is relative depending upon how the observer is moving. So let's talk about what this time is relative means. Suppose you're in a stationary vehicle. You have a mirror on one side, reflective surface, and you're going to shine light across the vehicle and back to yourself. The time it takes for this light to travel a distance 2D, so there and back again. The time it takes for this light to travel across and back again, we're going to call it a distance 2T. So if this light is moving at the speed of light c, and speed is equal to distance over time, and the light travels a distance 2T, or 2D rather, in a time 2T, meaning that the speed of light is this distance over time. And if I wanted to, then I could say that this distance is CT. Now, suppose instead you're going to do the exact same thing, but you're now in a moving vehicle. So you have the mirror across here, but by the time the light makes it across, the mirror is over here. You didn't aim the light that way. You fired the light straight out, but you're in a moving vehicle, so it was also headed that way at the same time. The light strikes here, and then it eventually makes it back down to here to be perceived by your timer or whatever the situation is. Your vehicle is moving at a speed v. This distance across to your mirror is still a distance d. It's still a distance d. But look at the length of the path traveled by the light. It is now longer. I'm going to call it a distance big D. And if we're paying close attention, this kind of looks like a right triangle. And I am going to call this distance x. So in the time that it's taken your light to travel 2D and back, we're going to call that time interval 2t prime. So the speed of light is equal to a distance 2 big D divided by 2t prime. So if I wanted to, similar to this math, I could call, because these twos cancel, I could call this distance c times t prime. But I could also call this distance, according to Pythagorean theorem, little d squared plus x squared. Is that reasonable? Well, certainly it is. That's the Pythagorean theorem. We know and love the Pythagorean theorem. So let's make some smart substitutions and see what we can see. This d is equal to ct prime. This distance we already know is equal to ct. What is x? Well, if velocity is equal to distance divided by time, right? Then this x is equal to v, the speed your vehicle is going, times t prime. Let's not forget that all these quantities are squared. And now, if we do a whole bunch of algebra, we are actually going to see that time is different in these two reference frames. that's a lot of math, but what are the implications of this equation? What is this equation trying to tell us? Well, if we look at that denominator, v squared over c squared will consistently be less than 1. 1 minus something small, but greater than 0 is going to be a positive value. We are consistently dividing time in the stationary reference frame. T is time in the stationary reference frame. We're consistently dividing it by something smaller than 1, which is going to make that entire quotient greater than the original value of t, meaning that t prime, or the time in the moving reference frame, will consistently be longer. In other words, time is moving more slowly in the reference frame that is moving. But math doesn't prove anything. This equation predicts a behavior that we have actually experimentally observed. We've actually taken atomic clocks that are running off of, the decay rate of an atom, and we have left one on the ground stationary and sent one off in a moving vehicle, moving at a high speed. And we've run these trials, and when the clocks return to each other, the clock that was moving actually hasn't passed as much time as the clock that remained on the ground. So we have, in fact, observed this to be a thing that occurs. Time dilation, or the idea that time in a moving reference frame goes more slowly, is actually something that we have proven, not at the speed of light or approaching the speed of light, but at higher speeds. The military/astronaut brothers, the Kelly twins, the one brother went off into space for a long period of time, and upon returning, he and his brother actually joked that while they had been previously 6 minutes apart, they're now 6 minutes and 5 milliseconds apart because of the time that one of them spent in space. So just kind of a funny thing. So there are other implications to this. Length contraction is a thing that we talk about. If time becomes longer or moves more slowly in a moving reference frame, then everything lengthwise also gets much shorter in that moving reference frame. Now, the math to prove this equation that describes the behavior is known as a Lorentz transformation, and it's a bit more complex math than we're ready to do here in this summer program. But we do have a great video, though, that I found online that tries to help you visually understand why length is contracted. And I am not going to take credit for it. I am going to show it to you so that you can see somebody explaining it, I think, pretty well.
Doing dynamics in space is fine, but you miss a lot of intuition that way. Adding a time axis changes everything. This is a space-time diagram. The rocket is still moving directly to the right in space. That upward motion you're seeing is only through time. Space-time is what we'd call a hyperbolic geometry. Anyone's first exposure to hyperbolas is usually with conic sections. It's what you get when you slice a cone parallel to its height. The Minkowski space-time in special relativity is a hyperbolic geometry. The x-axis is space, and the y-axis is time. This minus sign makes it hyperbolic. In fact, these hyperbolas would be the paths of something accelerating. Just remember, we've suppressed the other two space dimensions. These accelerating rockets are only moving left and right, not up and down. The up and down direction is time, not space. Anything stationary follows a path that lines up with the time axis. Anything moving steadily follows a straight path. Anything accelerating follows a hyperbolic path, because hyperbolic geometry. The axes are not absolute, though. These belong to our space station, but these belong to Rocket Clone. Notice how the time axis lines up with his path now? The angle that a path makes with the time axis tells you the speed of that thing in that reference frame. I repeat, speeds are measured as angles. Small angles are slow. Large angles are fast. Angles close to 45 degrees are near the speed of light. That last bit is going to be very important because before we can understand how length contraction happens, we need to define length first. Length is the space-time separation between two events that occur at the same time. Just that not everyone agrees on which events happen at the same time. Remember, grid lines that line up with the space axis are all the events that happen at the same time. If two observers have different space axes, they'll disagree on which events are connected. Since the events that define length have to be simultaneous, they'll disagree about length too. And space-time diagrams allow us to predict what those lengths will be. If we measure the length of the rocket, we would use these two events, because for us, those happen at the same time. If Rocket Clone measures the length, he would use these two events, because for him, those events happen at the same time. You can see right away the lengths are different.
Okay, so if we look at this equation for length contraction, we see that big quantity under the radical again, right? The 1 minus v squared over c squared, all under a square root. This is sometimes abbreviated with a gamma, that gamma is equal to the square root of the quantity 1 minus v squared over c squared. Sometimes v squared over c, sometimes v over c is sometimes just called beta. So just when you're reading things and you find different notations, that might be what you're looking at. But here it is again, 1 minus the quantity v squared over c squared, where v is the velocity of the moving object. Again, these are inertial reference frames or reference frames that are not accelerating. So you're in a reference frame that is moving near the speed of light, v, moving at some velocity v that is near the speed of light. If we compare that to the speed of light, square everything, subtract it from 1, you're again going to get something that is less than 1. But now instead of dividing it into time, we're multiplying it against the length of the object in space that is moving. And that actually results in something smaller. The object actually looks shorter. So objects moving near the speed of light in an inertial reference frame or a non-accelerating reference frame, time will pass more slowly to them and they will appear to be shorter to those in a stationary reference frame. So we can get into a discussion about inertial reference frames and who is the one that is actually moving. If you're moving away from me at 90% of the speed of light and I'm stationary, who's to say that you're not still and I'm moving away from you at 90% of the speed of light? You've perhaps heard some of this when we talk about how the universe is expanding and everything is moving away from everything, right? Is the entire universe moving away from us, or are we moving away from other things? It's an interesting question and quantity to answer, but it is that sensation that we get when we're in the car and we're stopped and the car next to us begins backing out. There's that reference again. And we suddenly feel like, oh my goodness, I'm still moving forward. Relative to them, you are moving forward. But also, relative to you, they're moving back, right? So it actually turns out that this math works both ways, which is a mind-blowing thing, that if I considered the spaceship to be the stationary object, then it would perceive me with all of these relativistic shifts. And if I consider me to be the stationary reference frame, I consider it to be the thing with all of these relativistic shifts. So that is a thing that kind of breaks the brain a little bit. Okay, so you're moving near the speed of light. Time is slowed for you. Things have gotten shorter. And you're looking at all of this and you're saying, this is why this is called a theory, Mary, because none of this could possibly be true. It's just a theory. Well, again, except that we've experimentally proven aspects of this. And in order for GPS to work, it actually takes into account relativistic shifts in time so that it can actually figure out where you're located. So this is actually work that we do and we apply so that we can make things like GPS function properly. So before you get all, this isn't real, this couldn't possibly be true, it's only a theory, please remember that when scientists say theory, we're talking about a well-vetted concept that reliably describes how things work. We just haven't been able to test it at every nook and cranny. In other words, we haven't been able to directly observe speeds at the speed of light, right, for objects with mass. We have been able to observe a lot of this when we take a look at the life of subatomic particles and cosmic rays in those particles, which we'll talk about later in the week. But we have been able to observe light moving at the speed of light. So why do I bring up that important point of we haven't been able to observe objects with mass moving near the speed of light? As you approach the speed of light, it's going to become increasingly difficult to get you moving faster and faster and faster. You are asymptotically reaching the cosmic space limit, right? And so as you get closer and closer and closer, your acceleration becomes less and less and less. It becomes increasingly difficult to get you actually to the speed of light. Well, inertia, while we talk about it very often in terms of mass, it is in fact quite simply a resistance to a change of motion. So as you get closer to the cosmic speed limit or the speed of light, you in fact gain inertia. You are actually effectively becoming more and more and more massive as you move closer to the speed of light. So as your effective mass increases, as you require and absorb more energy to get pushed near the speed of light, we actually find that mass and energy almost become synonymous in definition. And that's Einstein's great equation, E equals mc squared, which basically states that the resting mass of a material moving at the speed of light will have mc squared in terms of the quantity of energy. It will have a quantity of energy that is equal to mc squared. And we're going to talk about that more in the coming days, but we're going to leave that right there for now. So this presentation has encompassed about as much as I can cram into a video on special relativity. I know that it is a lot to process. Special relativity applies to the physics of objects moving at a constant velocity near the speed of light. General relativity will apply to accelerated reference frames, and Ryan will talk about that later this week. This presentation was not meant to make you an expert on relativistic physics, but rather to give you a first exposure. We'll have a discussion on this later this week. Hopefully, your brains and your imaginations have been stretched a little bit by this talk, and I'm looking forward to chatting with you more about this later this week. Thanks very much. Bye-bye. Again, prior to Einstein, Michelson-Morley, take two. Michelson-Morley, take three. Take four. Okay. Then, reflected mirror. Well, that was fun. What does it mean?